Welcome back to more discussion of the law of sines. So here's the setup for this case. Once again, we have two angles and one side. So we're going to do law of sines. Now this is a setup with a cell tower, a radio tower, some sort of tower that is being partially supported by these guy wires that go down to the ground. And there is tension upon these wires that keep the tower vertical. They're not exactly set an equal distance apart because in the real world sometimes you have streets or other things that interfere, or the soil on either side is different, so you have to be careful where you place it, so you're actually going into rock that will hold the guy wire into place. So let's see how we can analyze this using the law of sines. Now, we usually use capital letters when referring to vectors, but since I'm going back to using the law of sines, and I have indicated that the sides are small letters, I'm going to switch that capital T vector to a small t side, and the side opposite that small t will be a capital T. If that confuses you, just erase what you see up here at the top and deal with what you have at the bottom. But this is the tension. The most important thing we're going to look for in this triangle, although we're going to solve the whole thing, is the tension in that guy wire, because that would be your real world problem. What tension do we need there to hold the tower upright? Now I have added all the information we have, both in my simplified diagram and in the chart of all the parts of the triangle. So let's go ahead and start. Do we have any row in our chart that is the same? Or on our diagram, do we have a side and the angle opposite that are filled with numbers? No, we don't. So we have to do something else. We can once again find the missing angle here, angle A, by doing 180 degrees and subtracting the other two angles. And we find that angle A equals 38.7 degrees, which we could also put in over here on the diagram. All right, now that we have that, we have established a row here that has both a side and an angle listed, and we can now build a ratio from that. So here's the ratio of the side over the angle. As you can see, I've dropped both of the units. I'm going to remember to keep my calculator in degree mode. So as I'm doing the calculations, I'm okay if you happen to drop the units, just to save yourself some time writing and worrying about dropping a unit in the process. Just make sure you report the correct units when you are done. And from that ratio, I have built a proportion. And remember that a proportion is just two equivalent ratios separated by that equal sign. All right, so now I have chosen to work with this angle B because it is the largest, and I have set up my proportion with side B over the sine of that angle B. Then we cross multiply and solve. There is the result of my cross multiplication, and once again I'm going to be dividing both sides by that sine of 38.7 degrees to isolate B. Now notice that our 850 newtons has that bar over the zero, which is another way of showing that that zero is significant. So there are 3 or 4 significant digits in each of our original numbers that we were given. So we're going to report our final answer here in 3 significant digits, and we hold the place of that 9 with a 0. And that's it. And the units then are newtons. All right, so we have 1,310 newtons for that value. Now we rounded that, right? So when we go to find the tension in the wire that remains, we are not going to use that number, that rounded number. Now I showed you how to do this in the way that will get you through solving the entire triangle. However, the question on this word problem was actually, what is the tension in that wire? So in order to just get that information, you could have skipped the step I just did and done the one I'm about to do. So there's our ratio. Side A over the sine of angle A equals side T over the sine of angle T. Cross multiply and you get this. When you isolate T, You then find this, 850 sine of 35.7, and because you have divided both sides by the sine of 38.7, it canceled on the left-hand side, and you're left with this on the right-hand side. You see the angles there are almost the same, but just not quite. And our calculator gives us at the end 793 point blah, 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 blah. And we round it to 3 significant digits and put the units in. 793 newtons. That is the tension. And that is what we were looking for, 793 newtons. So ultimately, this is your answer. However, you also found this. You solved for it. You solved for this. You have solved the complete triangle if you followed my steps. If you just skip to this step, you still have your answer to the problem. How much tension should be applied to that guy wire to hold the tower upright? And let's move on to case 2. Now we have the case of two sides and the angle opposite one of them. This is not side angle side, it is angle side side. And this discussion will show you why you cannot use ASS to prove triangles congruent, because there are two options if you have ASS. Okay, so here's case 2. So one angle and two sides, the angle being opposite one of those sides, might look like that. It might also look like this, where you have an angle right here. So there's the angle, and you have a side of a given length. So there's side 1. And to finish that triangle, you must remember, we don't know how long that side is. We're not being given that information. We're being given an angle, a side, and one of those sides has to be opposite the angle, so the other length we must be given must be there. So if that side is exactly that angle, or that length, and we can then extend this bottom line however long it needs to be to meet that, and look, we have a right triangle. So that's another case that you might have when you have angle side side. But let's look at a third case. If you have an angle, okay, and we don't know how far that extends yet, but we know this angle, that's angle A, and we know this side, we're given a length, we draw it out properly, and then we're given another side, and that's the length of that other side. Note that we can't move this side up to meet side 2, even if it were longer, because if we move it either way, we're going to change the measure of angle A. So we can't move that one, nor can we stretch side 2 because we are given a length. So all this side 2 can do is swing back and forth. You're never going to have a triangle in that case. Let's look at another case. Let's look at the case where we have the angle, a side 1, and a side 2 that is longer than side 1. Okay? That could still work because we could extend this side as far as we need to meet the two sides that we have. We just have to figure out what that side is later. But we have a triangle. Now, this example and this example look kind of similar, but there's a very important difference. And to show you that difference, I'm going to copy this triangle. In fact, I'm going to copy it twice and move it down here so you can see both of them before I finish. Now, what I'm going to do is say, well, we don't have, notice, we do not have the top angle, as I'm showing you on the original copy. So if we don't know what that angle is, this side 2, may not be in that position. If you swing it around, keeping the same length, maybe it was really supposed to be in that position. So those are two different triangles with the same original angle, the same side 1, length of side 1, and the same length of side 2. Side 2 is just in a different position. It gives us two completely different triangles. They are obviously not congruent, but they do have the same two sides and the angle opposite one of those sides. That's why you can use ASS for solving triangles, but you cannot use it for congruence. However, if you do have angle side side, that means you have to solve both triangles. A little more complicated, more steps, but we start the same way. So let's look at some examples of each of these. Here's our first example. We have an angle A of 30.0 degrees. Notice that's 3 significant digits. Opposite that angle is side A with 10.0 meters. The units are over in the chart to the left. And side B of 20.0 meters. The only pair of side and opposite angle that we have is our A's, so let's start there. I have set up my length of side A over the sine of angle A on the left-hand side, and on the right-hand side I have the length of side B over the sine of B, because we don't know what B is yet. So now we will just cross multiply. So that gives us 10 times the sine of B on the left and 20 times the sine of 30 on the right. We still have a multiplication on the left, so we are going to divide by what we need to divide by to isolate that B. And when we do that, you can either put that into your calculator as you see it is there, or you can notice that if you divide 10 by 10 you get 1, and you divide 20 by 10 you get 2, and then you can put that into your calculator, just 2 times the sine of 30 degrees, and it's much simpler. However, let's do something a little bit different here. Let's not evaluate that yet. We're not done. We are not to our answer of B. So let's keep everything in the calculator and just do the next trigonometric step, which is to take the inverse sine of both sides. And that leaves us with B equals 90, or 90 degrees, because we're solving for the angle in degrees. So I need to adjust my drawing. I now know that I need to swing that side down so it forms a 90-degree angle with this side, which I can now extend. Please note that if B is 90 degrees, there is exactly one triangle that can be formed with one of the angles 30, its opposite side 10, the side opposite the right angle being 20. This should start looking familiar to you. But the point is, if you find an angle of 90 degrees within your triangle, there is only one solution for that triangle. Since angle A is 30 degrees, angle B is 90 degrees, we know that angle C must be 60.0 degrees. So we found that. The only thing we have left to find is the length of side C. Once again, for our first ratio, we return to the values we had at the beginning of the problem, and we cross multiply. To isolate C, we must divide by sine of 30 degrees on both sides, and when we appeal to the calculator and report the proper number of significant digits, we come up with 17.3, because our units of measure are meters. That is our final missing piece. 17.3 meters is the length of side C. The triangle is solved. So please look for part C in this discussion of the law of sines.